Myself Netra, studying in Sri Venkateswara College of Engineering, Bangalore. Today in this video, let us go through categorical semantics of probabilistic programming languages, which comes under theory of computations. First, moving on to abstract, stochastic memoization is a key high-order concept in probabilistic programming, particularly useful in Bayesian non-parametric. This approach allows us for extending models beyond their parametric constraint and combining them in a flexible, elegant way. While simple and practical stochastic memoization has proven difficult to fully understand, especially regarding how it interacts with data flow transformation. A straightforward implementation typically involves using the state monad, which lacks a commutative. This raises the question of whether stochastic memoization preserves the data flow property. That is, we can reorder the line of a program without altering its meaning as long as the data flow structure remains intact. In this video, we offer both operational and categorical semantics for stochastic memoization and name generation within a minimal probabilistic programming. Though our focus is limited to a specific class of functions, our main contribution is the first model of stochastic memoization for a constant binomial function over a non-enumerable type which supports data flow transformation. Introduction. Bayesian non-parametric models offer a flexible and powerful approach to statistical learning. Unlike parametric model, which have a fixed number of parameters, non-parametric model allow for an unbounded number of parameters that can grow as needed to fit complex data. This complexity enables them to capture subtle parameters that subtle patterns that parametric models might miss, making them more adaptable and scalable. Paramet Probabilistic programming provides a useful, powerful framework for implementing non-parametric model. One particular useful technique in this field is stochastic memoization. This paper or this video explores the semantic foundations of stochastic memoization. Stochastic memoization. In deterministic memoization, a function is computed once for a specific argument and the result is stored in a memo table. When the function is called again with the same argument, the stored result is returned, which improves performance but does not change the function's behavior. Example of non-parametric clustering with noise. A simple example of stochastic memoization is in a non-parametric clustering model. Suppose we have a set of individuals and want to group them into a cluster with unknown attributes. For instance, we might assign clusters based on Brexit support, geographic data, or salary. A common approach is to use a Dirichlet process with memoization. This process involves randomly assigning individuals to clusters using a distribution such as the normal distribution for cluster identifiers. Assigning attributes to clusters, for example, using a Bernoulli distribution, we can assign the value true to a cluster identifier with a probability of 0.5. This process defines the clustering structure, while the stochastic memoization ensures that the same cluster receives the same attribute assignment every time it is squared. Challenge. This paper or this video addresses the challenge of making the following components consistent. A type A with a diffuse probability distribution, a type for Boolean value that is true or false with Bernoulli distribution, a type for function from A to Boolean values. Stochastic memoization of constant Bernoulli functions, support for the data flow property, a key feature for optimizing programs and reasoning about their behavior. Traditional measures through theory struggles to handle this combination of components, but probabilistic programming languages can implement them effectively as they are essential for Bayesian modeling. This paper or this video's goal is to extend the semantic analysis of stochastic memoization to a broader range of domains, providing a clearer theoretical foundation for its use in probabilistic programming. Simplification through name generation. To simplify the model and avoid measure theoretic complications, we draw a parallel between diffuse probability distributions and name generation. In some cases, generating unique name as in a freshness property behaves similarly to drawing from a diffuse distribution. By using categorical models of name generation, we sidestep some of the complexity of measures through focusing on a minimal working example that demonstrate the core ideas of stochastic memoization. This video provides the groundwork for further extending the capabilities of stochastic memoization to more general types and models in Bayesian non-parametric statistics and probabilistic programming. Finite, countable, and diffuse domain. Finite domain. Memoization with a finite domain is straightforward, such as in the case of Boolean function. The memoization can be implemented by evaluating all possible values and store the result in mapping. Countable domains. For countable domains like integers, memoization corresponds to generating an finite stream of random values which can be thought of as a sequence of random choice. This is useful for models like Poisson process, where the gaps between the events flow and exponential distribution. Non-enumerable domains. For uncountable domains, the concepts of diffuse distributions become relevant. A diffuse distribution ensures that two draws from the distribution will never be equal. This is more complex to implement due to impossibility of enumerating all possible values and often requires stateful memoization techniques. Data flow property. Memoization must preserve data flow property, meaning program lines can be reordered or distracted as long as the overall program logic remains intact. This property is vital for program optimization and maintaining the commutability and of probabilistic function. Semantic interpretations. Memoization can be understood using different semantic models based on the nature of domains. Finite domains. Denotational semantics using strong monals over sets, countable domains, measurable space under Curie monad, diffuse domains. The challenge here lies in the handling uncountable spaces where traditional memoization techniques using tries do not apply. Denotational semantics. In this section, we introduce a denotational model that satisfies the data flow property, supports memoization of constant Bernoulli function, and is sound with respect to the operational semantics presented. This confirmed that consistency of criteria. Memoization relies on memo table, which can be seen as a form of hidden or local state. Our semantic domain is inspired by other models of local state, using a possible world's semantics in the form of functure category. Actions of morphism. The monad action of morphism between digraphs is complex, incorporating mappings over probability distributions and state extension. Data flow property. The monad satisfies the data flow property. It is strong, communicative, and affine. Conclusion. In this work, we explored the categorical semantics underlying probabilistic programming languages, emphasizing the significance of well-defined framework for understanding their behavior. By adapting a categorical perspective, we demonstrated how various constructs within these languages can be modeled using advanced mathematical structures, providing insights into their operational and denotational semantics.